Welcome back guys to another video for our AP Calc BC/AB review. Now I would just like to point out that the consistency on my channel has been absolutely amazing. If I had to graph the productivity of my videos against time, it would probably show up as the most continuous function you've ever seen in your life. Just kidding, there'd be a lot of jump discontinuities here and there and probably a lot more to come. But with that being said, the format of my videos are going to change kind of. To be actually geared towards the textbook I'm using in class, hence why there's a 4.1 here, because it's on chapter 1 lesson 4 of my textbook. And I will eventually go back over breaks and reread the textbook and make videos of all the chapters prior to chapter 4, if time allows it. But for now I'm just jumping into chapter 4 because that is where I am in class on the applications of derivatives unit. So today's video we'll be talking about extreme values, but I won't be focusing on the actually mathematically or analytically finding it, just to kind of understand from a visual standpoint and clarifying their technical definitions. So when I have an extreme value, I'm either referring to the highest or lowest y value in a function. Now these could be either global, also known as the absolute extremes, meaning they are the highest or the absolute lowest in the entire domain of that function. Or they could be local, also known as relative extremes, meaning that they're extreme values only compared to values nearby it on the graph. So for global maximums, the highest values in the entire domain of a function, if I had a x value at x equals c, then the global max is saying that the y value at c is only a global max if the y value f of c is greater than or equal to all other y values in the domain specified. Now for it to be a global minimum, the opposite applies. The y value at c has to be less than or equal to every other y value in our domain that they have given us. So we're gonna start off with a really simple example of a parabola, f of x equals x squared. If I were to ask to find my minimums and maximums, well, my minimum will be right here, and that is actually my only minimum. It is my global minimum. Also, important note right here, global extreme values are also local extremes, but the opposite doesn't work. And the reason being that if something is is an extreme value in the entire function, then it's definitely going to be extreme compared to the values nearby it. So your global extreme is technically the highest or the lowest of out of your list of local extremes, depending on whether you're finding maximum or minimum. So when I'm saying that the global minimum here is at x equals 0, that's my global minimum, but it's also my only local minimum. Now if I'm asked to find the maximums, well, there is no definite value for a maximum because on both sides it approaches infinity and the domain is all real numbers. But if I were to restrict my domain to from only a closed interval from 0 to 2, remember the brackets mean it's a closed interval, meaning it includes 0 and 2, well then my graph, instead of looking like this, would look more like this along the red line. So now we're just focusing on the red part, which is my domain that the question has specified. My minimum is still at x equals 0. My maximum now, my highest y value is right here at x equals 2. This is the highest in that interval, so it is my global max, and like I said earlier, globals are also locals. So this is my only local max, but it's also my global max. It's my only local min, but it's also my global min for the function of x squared with where my domain is a closed interval from 0 to 2. Now notice how I didn't have a maximum and a minimum until I made this a continuous closed interval. So right here down here we have what is called the extreme value theorem. Extreme value theorem. And what it's basically saying is that if a function f is continuous on a closed interval ab, then the function has both a max and a min value that is within that interval. So essentially what I've shown here, our a would be 0 and b would be like our 2. We had both a min and max, like I said, because it's in a closed and continuous interval. Keywords here is that it's continuous and that it is a closed interval, not an open interval. like this. If it was an open interval, the theorem does not apply. So let's just look at more examples. If I was looking at this right now, my global or absolute extreme values would be right here because that is the highest y value, and right here would be my global min because that is my lowest y value. Now as for the relative or local extremes, well, I'd have a local max here because that is the highest y value in this general area. This would be a local min, and this would also be a local min. Now also note that my endpoints in here were considered extreme values just because they're closed and they're included in that domain. The reason, if these were open and they were not included in the domain, I could not count the endpoints as extreme values. Now, later this will make more sense when we're actually calculating it, but I would like to break down the sort of hierarchy of extreme values. So, if something is an extreme value, it could either be at a endpoint, well, a closed endpoint, or it has to be a critical point. Now, what I mean by critical point, we'll be calculating this in a later video, but critical points are defined as where either the tangent or the derivative of that point has a slope equal to 0, or the derivative at that point is undefined. But it is still, the actual main function itself would still be defined. The function itself is still defined, but the derivative must be either 0 or undefined for it to be considered a critical point and a possible extreme value. So if you actually look at our graph here, we see, well, these are closed endpoints, so that's why the category they fit under. But over here, the tangent at this line is poorly drawn, but is actually a slope of 0. It's a flat horizontal. Same goes right here. The slope is 0 of the tangent. Now right here, this is a cusp actually, so there is no derivative at this point, hence it is undefined at that point. And hence these are critical point and these are endpoints and our 5 extreme values. Now, important note, all extreme values are, if they're not a closed endpoint, they must be a critical point. But not all critical points will necessarily be extreme values. For example, if I had a graph where my function actually looked like this, as poorly drawn and rushed, but if I were to look at this point, again poorly drawn, but my tangent of the derivative at this point you'd find would be 0. But notice how you can obviously tell that this is not a max or a minimum. You know, we have values higher than it on this side and lower than it on this side, and so it can be an extreme value, even though if we mathematically did this, we'd find that the tangent f of f prime x at this point is equal to 0. Now that being said, so all extreme values, if they're not an endpoint, closed endpoint, must be critical points, but not all critical points will necessarily be extremes, and we'll later calculate this using the first derivative test, like I said, in a later video. So that's pretty much it for this video. Now let's just look at some weirder examples. I want to find the absolute extremes in each of these 4 examples. So we have an easier example here. It's a closed continuous interval. Our highest y value, or our global max, would be right here. Now our global min, that would actually be right here. That is our lowest y value. Now for our next example, our global max, again, would be right here. Now, as for our global mins, well, these are both, if you can't tell, they're on the same y level. But notice how they're open intervals. So technically our min is somewhere here, or somewhere here, but because it's an open interval and not a closed interval, we can't really point towards a definite number, you know? Like if this was, for example, in the open circle at a height of 2, well, our min would technically be something along the lines of 2.00001, or who knows, whatever. It's indefinite. So since it's not definite, there is no min, global min, in this function. We have a global max, but not a global min. Again, this goes back to the extreme value theorem. We will always have a global max and a min when it's on a closed continuous interval. The fact that this is on an open interval means it does not stay consistent with that theorem. Now for our third example, same thing from before. It is not definite over here, even though technically our highest y value is somewhere among there, but we can't pin it down exactly, so there's no absolute or global max. Now as for minimum, again, it's technically somewhere here or here, but it approaches this open circle, but because the domain does not include it, there is no definite value for it, so there is no global min. And fourth example, now our lowest y value or global min is right here. Now as for our global max, now again, even though it's not consistent with the extreme value theorem, over here is still a critical point, and it is the highest point, so it is our global max. And yeah, that's pretty much it for this video. So I'll see you guys next time, where we'll probably talk about the mean value theorem or the first derivative test. Who knows? Well, see you guys next week, or hopefully. Bye.